Welcome to Chapter 5, Asphalt Materials. In this chapter, we will dive into the properties and behavior of asphalt materials, mainly focusing on their role in pavement design. Asphalt is the binding material that holds aggregate together, forming the surface of most modern roads. Understanding its chemical, physical, and mechanical properties is important for designing pavements that last under various environmental and traffic conditions. Let's start with the basics. Hot mix asphalt, also known as HMA. HMA is the most common material used in constructing the surface layers of asphalt pavements. It consists of an asphalt binder, aggregates, and sometimes some chemical additives to improve performance. The asphalt binder is a blend of hydrocarbons derived from the distillation of crude oil. Its composition and properties are key in determining the durability and strength of the pavement. In the US alone, we use around 30 million tons of asphalt in highway construction every year, highlighting its importance in infrastructure development. Our understanding of hot mix asphalt goes beyond just its components. It extends into the chemistry and rheology of asphalt binders, which we will explore further. Asphalt binders are complex chemical compounds. The binder's performance is deeply connected to its molecular composition, which determines how it interacts with aggregates and additives in a pavement mix. In this section, we will explore the chemistry behind these interactions and introduce a model for the chemical composition of asphalt binders. By understanding the chemical structure of asphalt binders, we can predict how the pavement will perform under different conditions such as heat, stress, and aging. At the molecular level, asphalt is composed mainly of hydrocarbons, which are molecules made of hydrogen and carbon atoms. These hydrocarbons can be categorized into different types of structures, including aliphatic structures, which are straight or branch chains, aromatic structures, which consist of unsaturated rings, and saturated rings or branches involve more complex molecular configurations. The strength and performance of asphalt come from the strong covalent bonds that hold these hydrocarbons molecules together. These bonds influence the overall viscosity, elasticity, and stability of the asphalt binder. In addition to hydrocarbons, asphalt binders contain a small amount of heteroatoms. Atoms other than carbon and hydrogen, such as nitrogen, sulfur, oxygen, and even metals. These heteroatoms have a significant influence on the interaction between asphalt molecules, altering its properties. The presence of metals can help identify the source of the crude oil used to produce the asphalt binder. Additionally, the proportion of heteroatoms affect how asphalt behaves when exposed to stress, heat, and environmental conditions. Asphalt molecules can exhibit polarity, meaning that they have uneven charge distribution. This polarity increases the interaction between molecules, particularly through electrostatic forces. Asphalt's molecular interactions can occur through either moderately strong electrostatic forces between polar molecules or through weak forces such as van der Waals forces between nonpolar molecules. Polarity plays an essential role in the binder's performance, especially in terms of adhesion to aggregates and resistance to moisture. Asphalt's behavior is also heavily influenced by temperature and oxidation. When the temperature rises or stresses are applied, the intermolecular bonds weaken, which can affect the binder's viscosity. However, intermolecular covalent bonds remain strong, maintaining the basic structure of the asphalt molecules. Oxidation, on the other hand, chemically alters the structure of asphalt by increasing the polarity of molecules, which leads to greater molecular association. This process makes the asphalt more brittle and therefore more prone to cracking over time. The Western Research Institute developed a model to explain the chemical behavior of asphalt binders, focusing on polar and nonpolar molecules. The polar molecules tend to associate more strongly with each other, forming a matrix, while the nonpolar molecules are dispersed within this matrix. Temperature has a significant impact on this behavior. As temperature increases, the polar molecules dissociate, leading to a less viscous material. As temperature decreases, these molecules associate more tightly, increasing the binder's resistance to flow. An asphalt chemical model aims to explain and predict the behavior, properties, and performance of asphalt binders based on their chemical composition and reactions. Since asphalt is a complex mixture of various hydrocarbons and other organic molecules, understanding its chemical makeup helps improve its application in road construction, especially in terms of durability, resistance to aging, and environmental impact. Asphalt is composed of various fractions of hydrocarbons that can be broadly divided into the following categories. Asphaltenes are high molecular weight solid-like materials that provide structure and stiffness to asphalt. Maltenes, this fraction includes resins, aromatic hydrocarbons, and saturates. Maltenes give asphalt its viscous nature. Saturates are nonpolar aliphatic compounds that are mostly inert. Aromatics are slightly more reactive due to their ring structures, providing flexibility. Resins are polar compounds that contribute to adhesion and help bind asphaltenes into a stable structure. So, as it is already mentioned, in the asphalt chemical model, we can break the binder down into different components. Asphaltenes, these are dark brown solids that form the backbone of the matrix. Resins, these are dark semi-solids that coat the asphaltenes and help to bind them. Maltenes, a solvent phase that consists of oils, resins, and lighter compounds. The proportion of these components varies depending on the separation method and can affect the binder's performance, particularly in how well it resists deformation under load. Now we shift to understanding the rheological or flow properties of asphalt binders, which are crucial for predicting how the material will behave over time. Rheology is the study of how materials flow and deform under stress, and it's particularly important in asphalt because these properties change as the binder ages. Asphalt binders exhibit viscoelastic behavior, meaning they combine characteristics of both elastic solids and viscous liquids. This behavior is time-dependent, meaning the binder's properties evolve as the pavement is exposed to traffic and environmental conditions. In rheology, materials can behave in different ways under stress. Newtonian materials like water maintain a constant viscosity regardless of the applied shear strain rate. Non-Newtonian materials like asphalt binders exhibit viscosity that changes with the shear strain rate, which means they can behave differently under varying loading conditions. In asphalt, we see non-Newtonian behavior at lower temperatures, which means that As the shear stress increases, the viscosity changes. This is important when designing pavements as we need to account for this behavior to predict how the pavement will deform over time. Absolute viscosity, also referred to as dynamic viscosity, is a fundamental property that describes how a fluid resists flow when an external force or shear stress is applied. Essentially, viscosity represents the internal friction within the fluid, which works to resist movement. In the context of asphalt, absolute viscosity helps us understand how the asphalt binder will flow or resist deformation when subjected to traffic loads, heat, or cold. At its core, viscosity is calculated as the ratio of shear stress to shear rate. This means that the viscosity reflects how the material's deformation changes in response to the force applied. If the viscosity is high, the material resists flow, behaving more like a solid. If the viscosity is low, the material flows more easily, acting more like a liquid. In asphalt binders, viscosity is especially important because it influences how well the binder will perform in the pavement under both traffic loads and varying temperature conditions. Asphalt behaves differently at different temperatures. At high temperatures, the viscosity decreases, meaning the asphalt becomes softer and more fluid. Conversely, at low temperatures, the viscosity increases, making the asphalt harder and more prone to cracking. For pavement design, this relationship between temperature and viscosity is important. At high temperatures, a binder with too low a viscosity could help to rotting, where the pavement permanently deforms under the weight of traffic. This is often seen during hot summers when the pavement becomes soft and can't hold its shape. On the other hand, at low temperatures, a binder with too high a viscosity could become brittle, resulting in cracking, especially in cold climates. This is a major concern during winter months when the pavement contracts and the binder becomes too stiff to flex. In Newtonian liquid, all applied energy is dissipated in the form of heat. The liquid does not recover original condition after removing load. Behavior of the material is described by a single constant value of viscosity. In non-Newtonian flow, viscosity is not a constant value but a function of time. The non-Newtonian behavior of asphalt binder is studied using linear viscoelasticity theory. As mentioned, asphalt binders exhibit viscoelastic behavior. At high temperatures or low loads, the binder behaves more like a viscous liquid, flowing easily. But at lower temperatures or higher loads, the binder behaves more like an elastic solid, which can return to its original shape after stress is removed. The proportion of viscous and elastic behavior depends on the temperature and shear rate. When designing pavements, we need to understand how this balance shifts to ensure that pavement performs well in both hot and cold climates, as well as under varying traffic loads. Solid materials respond to shear strain in a manner that reflects their rigidity and elasticity. Solids have a definite shape and structure, meaning their molecules are tightly bound together which resists deformation. In terms of elastic solids, Materials such as metals, concrete, or asphalt, shear strain causes the material to deform but not flow. These materials can return to their original shape once the shear stress is removed, provided the stress does not exceed a certain limit, which is called the yield strength or elastic limit. The relationship between shear stress and shear strain in elastic solids is typically linear and is described by Hooke's law, where tau equals G times gamma. Tau is the shear stress, G is shear modulus, and gamma is shear strain in this equation. This equation shows that shear strain is directly proportional to the applied shear stress. The shear modulus, or modulus of rigidity, reflects how resistant the material is to deformation under shear stress. In contrast to solids, liquids or fluids respond to shear stress in a completely different way. Liquids don't resist shear strain in the same way solids do, and they flow when subjected to shear stress. This flow behavior is known as viscosity, the property that describes how resistant a fluid is to flowing. In terms of Newtonian fluids, like water or air, the shear strain increases linearly with increasing shear stress. Newton's law of viscosity governs the relationship between shear stress and shear rate. Shear rate is the rate of strain in a fluid. This relationship is as tau equals eta times gamma, where tau is shear stress, eta is dynamic viscosity of the fluid, and gamma is shear rate or rate of change of strain. For non-Newtonian fluids, viscosity remains constant regardless of the shear rate. This means that no matter how much force you apply, the relationship between shear stress and flow remains the same, and the fluid flows smoothly without sudden change in behavior. The shear strain behavior of asphalt binders is important for understanding how asphalt reacts under the stresses imposed by traffic loads and environmental conditions. Asphalt binders, as viscoelastic materials, exhibit both elastic and viscous characteristics depending on the applied load and temperatures. Shear strain in asphalt binder is the deformation that occurs when a shear force, which is a force applied tangentially or parallel to the surface, is applied to the asphalt binder. In the context of pavement, shear strain becomes significant when vehicles apply loads to the road surface. The way asphalt responds to this stress will determine whether it deforms, as in rotting or permanent deformation, or recovers its shape, which is elastic behavior. Creep loading refers to the phenomenon where a material undergoes gradual, time-dependent deformation when subjected to a constant load or stress over an extended period. This is particularly relevant for asphalt pavements, which are subjected to prolonged stresses from traffic, especially in areas where heavy or slow-moving vehicles exist. In the context of asphalt, creep occurs when the asphalt binder slowly deforms under a constant load, such as a stationary truck or repeated traffic passes. High temperatures make asphalt more prone to creep as the binder becomes softer and less resistant to deformation. Over time, if the stress is high enough or the temperature is too hot, this deformation becomes permanent and can lead to rotting, which is a form of surface deformation where the pavement exhibits longitudinal depressions in the wheel passes. Creep behavior is important to understand because it helps predict how the pavement will deform under sustained loads and what kinds of permanent damage may result. In regions with hot climates and high traffic loads, creep can lead to permanent deformation if the asphalt binder is not designed to withstand such conditions. Creep compliance is a material property that quantifies how much a material deforms over time under constant load. It is a measure of the material's susceptibility to creep and is particularly important in evaluating how well asphalt binders and mixes can resist permanent deformation. Creep compliance is defined as the ratio of the strain that develops in the material over time to the constant stress applied. Mathematically, it is expressed as d as a function of t, epsilon as a function of t, and basically we do have um, a constant value of sigma in the denominator. So d as a function of t is a creep compliance at time t. Epsilon as a function of t is time-dependent strain, and sigma is constant applied stress. There are some key concepts in creep compliance. First, it is a time-dependent deformation. Creep compliance increases over time because the material continues to deform the longer it is under constant stress. Asphalt materials will initially resist deformation, but over time the strain accumulates as the binder flows under the stress. The second important key concept in terms of creep compliance is that a high creep compliance value indicates that the material deforms more easily under constant stress, meaning it has a lower resistance to creep. This can lead to permanent deformation like rotting in pavements that experience prolonged loads or high temperatures. A low creep compliance value means the material resists deformation better under constant load, and thus is less prone to creep. Asphalt binders with low creep compliance are more likely to maintain their shape under prolonged traffic loads and higher temperatures, making them ideal for regions with heavy traffic or hot climates. In asphalt pavements, creep behavior is a critical factor in predicting long-term performance, especially in areas prone to heavy loading or high temperatures. Asphalt mixes with high creep compliance can lead to permanent deformations such as rotting, which can form in the wheel passes of the road. They can also lead to fatigue cracking if the asphalt binders become too brittle after repeated cycles of creep deformation. In general, the material's viscoelastic nature plays a role in creep behavior. In the viscous phase, the binder flows under stress, leading to permanent deformation, while in the elastic phase, the material attempts to recover after the load is removed. At higher temperatures, asphalt behaves more like a viscous liquid increasing its susceptibility to creep. Relaxation loading refers to the reduction of stress in a material under constant strain over time. This behavior is characteristic of scholastic materials like asphalt binders, which exhibit both elastic and viscous properties. In contrast to creep, where strain increases under constant stress, stress relaxation describes how the internal stresses within the material gradually decrease while maintaining a constant deformation or strain. When a constant strain is applied to a viscoelastic material like asphalt, the material initially develops a high internal stress to resist the deformation, which is elastic response. However, over time, the stress relaxes as the material's viscous component allows it to adjust and flow slightly, reducing the internal stresses. This relaxation, this stress relaxation is due to the material's internal molecular rearrangements. There are two important components in this behavior. The first one is elastic component. The material behaves like a spring resisting deformation, which generates immediate stress. And the second component is viscous component. Over time, the material flows, and this flow reduces the internal stresses, leading to the phenomenon of relaxation. In asphalt pavement, relaxation loading plays a key role, particularly under conditions where the pavement is subjected to thermal stresses or cyclic traffic loads. In terms of thermal stress relaxation, we know that asphalt pavements are exposed to significant temperature fluctuations, which cause the pavement to expand and contract. During cooling, the pavement contracts, potentially creating tensile stresses. If the asphalt binder has good stress relaxation properties, it can gradually release these tensile stresses over time, reducing the likelihood of thermal cracking. This is particularly important in cold climates where asphalt is more prone to brittle failure. In terms of traffic-induced stress relaxation, we know that asphalt pavements experience repeated loading from traffic. After a load is applied, the material generates internal stress to resist deformation. Over time, however, the asphalt can relax these stresses. The ability to relax stress means that the pavement is less likely to accumulate damage from repeated loads, reducing the risk of fatigue cracking. Asphalt binders that exhibit better relaxation properties tend to perform well in resisting long-term fatigue damage. The axial relaxation modulus and the shear relaxation modulus are both important measures of how viscoelastic materials, such as asphalt binders, respond to stress relaxation over time. These moduli provide insights into the material's ability to relieve stresses under different types of loading. The relationship between these two moduli is grounded in the material's mechanical properties, and their behaviors are interconnected to the theory of viscoelasticity and elasticity. In linear viscoelastic materials such as asphalt, the axial and shear responses are related to Poisson's ratio, which is a material property that describes the ratio of lateral strain to axial strain when the material is stretched or compressed. In the case of viscoelasticity, Poisson's ratio is often considered to be time-dependent, and it can link the behavior of axial and shear moduli. For most viscoelastic materials, Poisson's ratio remains relatively constant over time, especially for incompressible materials like asphalt at certain temperatures. With a constant Poisson's ratio, we can derive a relationship between the axial and shear relaxation moduli. The relationship between the axial relaxation modulus and the shear relaxation modulus for isotropic linear viscoelastic material is given as G as a function of T equals E as a function of T, where G is the shear relaxation modulus and E is the axial relaxation modulus. So G equals E over 2 times 1 plus mu as a function of T. This equation shows that the axial relaxation modulus depends on both the shear relaxation modulus and Poisson's ratio. If Poisson's ratio is small, which is common in highly incompressible materials, the relationship simplifies slightly, but the general concept remains that axial stiffness is directly influenced by the shear stiffness. Sinusoidal dynamic stress loading is a type of mechanical loading used in testing asphalt mixtures, particularly in the dynamic shear barometer test, to evaluate the viscoelastic properties of the asphalt binders or asphalt mixtures. In this method, a sinusoidal or a wave-like stress or strain is applied to a material to simulate the repeated loads a pavement experiences from traffic. This type of loading is essential for understanding how asphalt behaves under real-world traffic conditions over time. Some key concepts in this type of loading: sinusoidal stress is a repetitive wave-like load applied to the material, typically altering between compressive and tensile forces. The stress is applied in a pattern that resembles a sine wave, with peaks and troughs representing maximum and minimum stress points. The stress changes cyclically over time and is characterized by its amplitude and its frequency. Amplitude is the maximum applied stress, and frequency is the number of cycles per second, typically in Hertz. Dynamic loading refers to the application of a load that varies over time, in contrast to a static load which remains constant. In the context of asphalt testing, dynamic loads simulate the real-world conditions of traffic loads moving over the pavement repeatedly. The dynamic stress applied during sinusoidal loading helps measure how asphalt materials respond to varying loads at different frequencies and temperatures. It should be noted that asphalt mixtures and binders exhibit viscoelastic behavior, meaning they show both elastic and viscous responses when subjected to stress. Under sinusoidal dynamic stress, the phase angle between the applied stress and the resulting strain is measured. The phase angle helps determine how much of the material's behavior is elastic versus viscous. So, as it is mentioned, the phase angle describes the lag between a stress and a strain. An increase in phase angle increases the viscous behavior and decreases the elastic behavior. For Newtonian viscous liquid, phase angle equals 90 degrees. For elastic solid material, phase angle equals 0 degree. For viscoelastic materials, phase angle is between 0 degrees and 90 degrees. So we already know that dynamic modulus and phase angle are both important fundamental properties to fully describe the viscoelastic response under dynamic loading. Both are function of the frequency of loading, which can be frequency or angular frequency. Alternative to describe dynamic properties of viscoelastic materials is storage modulus and loss modulus. The storage modulus represents the elastic component of the material's response to dynamic loading. It indicates how much energy is stored in the material during deformation and is subsequently recovered when the load is removed. The loss modulus represents the viscous component of the material's response to dynamic loading. It measures how much energy is dissipated as heat during each loading cycle, indicating the flow or viscous behavior of the material. So as shown on this slide, there are mathematical methods to relate the dynamic properties to the relaxation modulus and Curie compliance. So in other words, if one is known, the others can be calculated. The shear dependent viscosity is related to the shear dynamic modulus and the radial applied frequency as shown on this slide. We can also calculate the loss energy in a loading cycle using the equation shown on this slide. We already know that for elastic materials, there is no dissipated energy and delta equals 0 degree. For viscous materials, delta equals 90 degree and loss energy is the area in the loop. For a viscoelastic material, delta is a value between 0 degree to 90 degree, and this graph we show a delta value of 45 degrees and the corresponding area in the loop. It is important to note that stored and loss dynamic moduli do not correspond to elastic and viscous energy. The Burger's model is a mechanical model used to describe the viscoelastic behavior of materials such as asphalt under stress. It combines both elastic and viscous elements to represent how the material behaves when subjected to load, capturing both immediate elastic deformation and time-dependent viscous flow. The Burger's model is particularly useful in pavement engineering because it simulates how asphalt responds to long-term loading, which is creep, and stress relaxation. It combines two fundamental viscoelastic models, the Maxwell model, which represents viscous flow, and the Kelvin-Voigt model, which represents elastic deformation and delayed elastic recovery. The Burger's model is composed of four mechanical elements. Two springs represent the elastic deformation of the material. Two dashpots represents the viscous or irrecoverable flow of the material. So springs represent the recoverable deformation of the material. Dashpots represents the irrecoverable flow of the material. The springs and dashboards are arranged in series parallel configuration, combining the Maxwell and Kelvin-Roy models. The elements in this model include elastic spring, representing instantaneous elastic deformation. When a load is applied, the material deforms immediately and the deformation is fully recovered once the load is removed. The other element is viscous dashboard, which represents the permanent viscous flow of the material. This dashboard models permanent deformation that occurs under sustained loading and is not recovered after the load is removed. The next element is Kelvin-Roy model. This element consists of a spring and a dashboard in parallel, which represents time-dependent elastic recovery and delayed elastic deformation. When a load is applied, the material deforms slowly, but can recover some of this deformation after the load is removed. Asphalt behaves both elastically and viscously under traffic loads, making the Burger's model an ideal way to describe its response under different loading conditions. In other words, the first spring in the Burger's model accounts for the instantaneous elastic deformation that occurs when a load is applied to the pavement. This is recoverable, meaning that once the load is removed, the material returns to its original shape. The dashboard represents again the viscous flow of the material, which leads to permanent deformation or creep. In pavement engineering, this is important for understanding how asphalt pavements experience rotting or permanent deformation under sustained traffic loads. The second spring and dashboard model, this element models delayed elastic deformation. When a load is applied, this component allows the material to deform gradually over time, but also to recover partially once the load is removed. This is critical for predicting time-dependent recovery and stress relaxation in asphalt. So as mentioned in previous slide, asphalt behaves both elastically and viscously under traffic loads, making the Burger's model an ideal way to describe its response under different loading conditions. The first element in this model, elastic deformation, or the first spring in the Burger's model, accounts for the instantaneous elastic deformation that occurs when a load is applied to the pavement. As already mentioned, this is the recoverable part, meaning that once the load is removed, the material returns to its original shape. The second element is the dashboard. This dashboard represents the viscous flow of the material, which leads to the permanent deformation or creep. In pavement engineering, this is important to understand the rotting and permanent deformation under sustained traffic loads. The third element in this model is the delayed elastic deformation. In other words, when a load is applied, this component allows the material to deform gradually over time, but it also allows to recover partially once the load is removed. This is important to understand and to study the time-dependent recovery and stress relaxation in asphalt. So we already know that in viscoelastic materials such as asphalt binders, Viscoelastic properties are functions of time and temperature. In this type of materials, we can use time-temperature superposition principle. In other words, the effect of time on material properties can be replaced by the effect of temperature and vice versa. In other words, one of the most important concepts in asphalt rheology is time-temperature superposition. This principle helps us understand how asphalt binders behave over a range of temperatures and loading times. Essentially, asphalt's response to a stress at high temperatures can be similar to its response at lower temperatures over a longer period of time. This relationship allows engineers to use short-term laboratory tests to predict long-term pavement performance. For example, a quick test at high temperatures can simulate the effects of years of traffic loading in colder climates. Time-temperature superposition is a fundamental tool for predicting creep, fatigue, and rotting behavior in asphalt pavements. In asphalt pavement, the time-temperature superposition principle is used on experimental data to obtain master curve, for example. A master curve describes the viscoelastic properties at a reference temperature and over a range of time or frequency. This principle can also be used to obtain a shift function temperature curve, which describes the ratio between the actual time at which the test was conducted and the reference time to which the data is shifted versus the temperature at the actual time. A typical master curve for dynamic modulus would look like this. At high frequencies, simulating short loading times such as fast-moving traffic, the dynamic modulus would be high, indicating that the material is stiff and resistant to deformation. At low frequencies, simulating long loading times such as slow-moving trucks or long-term environmental effects, the dynamic modulus would be lower, indicating that the material is softer and prone to deformation. As temperature increases, the dynamic modulus shifts downward because the asphalt behaves more like a viscous material and is less able to resist deformation. Shift factors are used to align the data obtained at different temperatures and frequencies to create a continuous master curve. These factors allow the data at one temperature to be shifted horizontally along the frequency axis, allowing long-term predictions to be made from short-term tests. The master curve is typically constructed around the chosen reference temperature. Data from other temperatures are shifted horizontally to align with the reference temperature, creating a smooth continuous curve. The shifting function gives the relationship between the actual time and the reduced time for each temperature. Several testing protocols can be used to study the properties of asphalt binders at a wide range of testing conditions, loading conditions, and environmental conditions. Some of these tests include viscosity, penetration, dynamic shear, flexural creep, tensile strength, surface energy, and aging. Viscosity measures the resistance of a liquid to flow. In the context of asphalt binders, viscosity indicates how easily the binder flows at a given temperature. It is one of the most important critical properties used in evaluating the performance of asphalt binders under different temperatures. In terms of high viscosity, the binder is stiffer and flows less easily, which is beneficial at high temperatures to prevent watting, but can cause cracking at low temperatures. In terms of low viscosity, the binder is softer and flows more easily, which is beneficial at low temperatures to prevent cracking, but can lead to rotting at high temperatures. Viscosity is measured at a specific temperature, typically at 60 degrees or 140 degree Fahrenheit, to simulate in-service conditions, and 135 degrees C or 275 degrees F to simulate mixing and construction conditions. Viscosity helps determine the binder's workability during construction and its resistance to deformation under traffic loads. There are different testing protocols to study the viscosity of asphalt binders. These protocols are based on the standard methods as described on this slide for different types of viscosities, including absolute viscosity, kinematic viscosity, and rotational viscosity. In terms of absolute viscosity, the time that it takes for the binder to flow between two marks is measured. It is usually done at 60 C degrees, and the unit is Pascal second. In kinematic viscosity, the same principle to measure the resistance to flow under gravity is used. So there are different units for this viscosity. For example, Pascal second is one of them. This test is done at 135 degrees C. Rotational viscosity refers to the internal resistance of the asphalt binder to flow when subjected to shear force. This property is typically measured at high temperatures, which simulates the conditions during the production and laying of hot mix asphalt. High viscosity means that the binder is stiffer and flows less easily, which may make it difficult to mix and place the asphalt at the construction site. Low viscosity indicates that the binder is more fluid, which can make mixing and placement easier, but if the viscosity is too low, it may lead to issues such as segregation or bleeding. The penetration test measures the hardness or softness of the asphalt binder by determining how far a standard needle penetrates the surface of the binder under controlled conditions of time, temperature, and load. A softer binder or a higher penetration value allows for more flexibility, which is useful in colder climates to prevent cracking. A harder binder or lower penetration value provides more resistance to deformation, which is useful in warmer climate conditions to prevent rotting. In this testing protocol, the test is performed at 25 C or 77 F using a 100-gram load applied to the needle for 5 seconds. The result is expressed in tenths of a millimeter. For example, a 60-70 penetration grade, 60-70 penetration grade means the needle penetrates 6 to 7 millimeter. The penetration value is a traditional way to classify the binder's consistency and its ability to resist deformation under different temperature conditions. Dynamic shear modulus is a measure of the binder's stiffness under dynamic cyclic shear loading. This property is critical for predicting how the binder will behave under traffic loads, particularly in resisting rotting and fatigue cracking. Complex modulus in this test represents the total resistance to deformation, elastic plus viscous. Phase angle indicates the balance between the elastic recoverable part and viscous non-recoverable part of the deformation. A lower phase angle means the material is more elastic, while a higher phase angle means it is more viscous. There are different testing protocols. The common one, dynamic shear barometer, DSR, is used to apply a sinusoidal stress or a strain to a thin layer of the asphalt binder over a range of temperatures and frequencies. The results are used in the performance grading system to classify binders based on their performance at high and intermediate temperatures. G star and delta, shear modulus, and phase angle help evaluate the binder's ability to resist rotting at high temperature and fatigue cracking at intermediate temperatures. Flexural curve stiffness measures the resistance to deformation of asphalt binders at low temperatures over time. This property is especially important for predicting thermal cracking in cold climates, where binders can become brittle and prone to cracking. The bending beam barometer is used to measure the creep stiffness and M value, which is the rate of stress relaxation of asphalt binders at low temperatures, temperatures such as negative 12C or negative 24C. Stiffness uh, is one of the parameters obtained in this test, where a low stiffness value indicates better low temperature flexibility, reducing the risk of cracking. M value is another parameter obtained in this test. A higher M value indicates a binder that can better relax stresses at low temperatures, improving its resistance to thermal cracking. The BBR test is crucial for predicting the binder's performance at low temperatures and its ability to resist thermal cracking. On this slide, we see how we can calculate stiffness using the results of this test, BBR test. Stiffness is a function of applied force, beam length, beam height, moment of inertia, and beam width. Also, it's a function of deflection, which is a function of time. So on this slide, we see how we can calculate deflection as a time, and from having the deflection and other parameters, we can obtain the value of stiffness. On this slide, we observe how to calculate M value. And M value can be calculated using the equation shown on this slide, and for that we need to have the maximum stress and strain values. In this example, we learn how to calculate the stiffness of the material at every repeated time using the equations in previous slides. So we have information on the deflection of the specimen and the time of the test. There are also other information about temperature, load applied, beam width, beam thickness, and distance between beam supports. Basically, that is the beam length. So using these parameters, we can, and having the deflection values, By using previous equation on stiffness, we can calculate the stiffness value of the asphalt. So this slide shows the values of stiffness at different times, and basically the two equations that are used to calculate stiffness are shown on this slide. So we can use this information to plot the log stiffness versus log time. Tensile strength measures the maximum stress that the asphalt binder can withstand in tension before failing or breaking. This property is essential for understanding how well the binder can resist cracking, especially at low temperatures where the pavement experiences thermal contraction. The direct tension test is used to measure the binder's tensile strength and failure strain at low temperatures. The binder is pulled apart under controlled conditions until it breaks. Tensile strength provides insight into the binder's ability to withstand tensile stresses that lead to cracking, making it a key factor in preventing thermal cracking in cold environments. Surface energy refers to the energy required to create a new surface by breaking bonds between molecules at the interface of two phases. For example, between the asphalt binder and aggregate. Asphalt binder is one phase, aggregate is the other phase. In asphalt, surface energy affects the adhesion between the binder and the aggregate, as well as the binder's resistance to moisture damage. High adhesive surface energy improves the bond between the binder and the aggregate, reducing the risk of stripping, which is loss of adhesion in the presence of moisture. High cohesive surface energy increases the internal strength of the binder, improving its resistance to cracking and deformation. Surface energy in general plays a critical role in moisture sensitivity and overall pavement durability by ensuring strong bonding between the binder and the aggregate and resistance to moisture damage. There are different techniques and methods to measure the surface energy. Usually, surface energy is measured using techniques like contact angle measurements and surface tension testing. The Wilhelmy plate method can be used to determine surface energy for asphalt binders. In this technique, the contact angle between the asphalt binder and some probe liquids is computed and used to calculate the three components of surface energy. Aging is one of the critical factors that affect the long-term performance of asphalt binders. As binders age, they become stiffer and more prone to cracking due to oxidation and exposure to environmental factors such as heat and air. Aging occurs in two primary phases. Short-term aging happens during the production, transportation, and placement of the hot mix asphalt. It's a result of exposure to high temperatures and air while the mixture is being processed. Long-term aging takes place over the pavement's service life, as the binder is continuously exposed to environmental conditions like UV radiations, oxygen, and fluctuating temperatures. Aged binders lose their flexibility, which can lead to premature cracking, especially in colder climates where the pavement undergoes thermal contraction. The rolling thin film oven (RTFO) test simulates the short-term aging that asphalt binders experience during the hot mix asphalt production and construction process. In the RTFO test, a thin film of asphalt is spread inside bottles that rotate in an oven, which allows hot air to flow over the sample, simulating aging caused by heat and air exposure during mixing and laying of the asphalt. This test helps predict how the binder will perform after construction and is essential for determining the binder's resistance to hardening and cracking. RTFO age binders are typically used in further tests like the pressure aging vessel (PAV) test for long-term aging predictions. Asphalt binders undergo significant change in their physical properties as they age. Some of these changes include increased stiffness. Aging causes the binder to harden, which increases its stiffness and reduces its ability to accommodate movements due to temperature change or traffic loads. Decreased ductility is another change in the physical properties as asphalt binder ages. Aged binders lose flexibility and become brittle, making them more prone to cracking under tensile stress. Oxidation is another changes during the aging of an asphalt binder. Prolonged exposure to air leads to the oxidation of the binder, which increases its polarity and molecular associations, further contributing to hardening and loss of elasticity. These changes highlight the importance of selecting binders that can withstand aging while maintaining sufficient flexibility to resist cracking. The pressure aging vessel test simulates the long-term aging that occurs throughout the service life of the pavement. This test is conducted after the binder has undergone short-term aging in the RTFO. In the PIV test, the RTFO age binder is subjected to elevated temperatures and pressure inside the vessel, replicating the aging process that would take place over 5 to 10 years in the field. The PIV test helps predict the binder's long-term performance, particularly its susceptibility to fatigue cracking and thermal cracking. By understanding both short-term and long-term aging behavior, engineers can select binders that remain durable and flexible over time. Asphalt binders are graded and categorized to ensure that they can perform under specific temperature ranges and traffic conditions. Two of the most widely used grading systems are penetration grading, which is one of the older systems based on how deeply a standard needle penetrates the asphalt sample under controlled conditions, and viscosity grading, which is based on the flow properties of the asphalt binder. There are also some other advanced techniques, which are the common techniques used these days, such as performance grading technique (PG system), which is a newer, more comprehensive system that evaluates the asphalt binder's performance across a range of temperatures and under varying loads. Penetration grading is one of the oldest methods used to classify asphalt binders based on their hardness or softness. This grading system relies on a sample test that measures how far a standard needle penetrates the asphalt binder under specific conditions. The test is conducted at a temperature of 25°C or 77F using a 100-gram load for a period of 5 seconds. The result of the penetration test is expressed in tenths of millimeter. For example, a 60-70 penetration grade means that the needle penetrated between 6 mm and 7 mm. The penetration value gives an indication of the binder's consistency. A higher penetration value indicates a softer binder, while a lower value indicates a harder binder. Penetration grading is useful for selecting binders for moderate climates, but it doesn't fully account for the binder's performance at high or low temperatures. The system is simple and inexpensive, but it has limitations as it doesn't directly measure the binder's performance under real-world traffic conditions or aging effects. On the other hand, viscosity grading classifies asphalt binders based on their flow characteristics at specific temperatures. The viscosity test measures how easily the binder flows when subjected to stress, providing a more consistent and reliable indication of how the binder will behave under high temperature conditions, especially during construction and in service. Absolute viscosity is measured at 60 C or 140 F, which represents the typical high-temperature service condition of asphalt pavements. Kinematic viscosity is measured at 135 C or 275 F, which simulates the conditions during mixing and placement of the hot mix asphalt. Viscosity grading offers a more precise evaluation of the binder's behavior in hot climates, where rotting due to binder softening is a major concern. Binders are graded according to the ASTM D3381 and ASTM D2171 standards, with viscosity grades denoted as AC-5, AC-10, and etc., where the number represents the binder's viscosity and porosity. While viscosity grading provides better control over the binder's flow characteristics, it doesn't directly assess low temperature performance or how the binder reacts to aging over time. Viscosity of aged residue grading system, also known as AR grading, builds upon the viscosity grading system by incorporating the effects of aging. This system aims to predict how the binder will perform after it has aged in service. This provides a more accurate reflection of the binder's long-term behavior. In this system, the asphalt binder is first aged in the laboratory using the RTFO test, which simulates short-term aging that occurs during mixing and construction. After aging, the viscosity of the binder is measured at 60 C or 140 F. This gives an indication of how the binder will behave after it has aged due to heat and exposure to air. This system provides a more realistic assessment of the binder's performance after aging, making it particularly useful in regions with high temperatures or traffic loads where binder hardening due to aging can lead to cracking and fatigue failure. This system is, for example, this is commonly used in California and is part of the Caltrans grading system, where binders are denoted as AR-1000 or AR-2000 based on the viscosity of the aged residue. This system has its own limitations as well, like viscosity grading. The aged residue system is focused on high temperature behavior and does not directly measure the binder's performance at low temperature or its fatigue resistance. The performance grading system is the most advanced and widely used system for selecting asphalt binders. This system was developed as part of the SuperPav system and is based on the binder's ability to resist rotting, fatigue cracking, and low temperature cracking over a wide range of conditions. In this system, binders are graded according to their high temperature and low temperature performance. For example, a PG64-22 binder is designed to perform well at high temperatures up to 64 C and low temperatures down to -22 C. PG binders are selected based on the climate conditions they will be exposed to and the traffic load the pavement will carry. By accounting for both temperature and loading, the PG system provides a much more accurate method of selecting binders that will last longer and perform better under real-world conditions. In SuperPav performance grading system, different tests are involved to grade the asphalt binder. These tests include rotational viscosity to study the workability of asphalt binder, DSI or dynamic shear barometer on unaged, RTFO aged, and RTFO plus PAV aged asphalt binders, BBI bending beam barometer on RTFO plus PAVH binder, and direct tension tests. This table shows the different tests that are involved in performing SuperPav performance grading system. As mentioned in previous slide, there are different types of tests including rotational viscosity, DSR, BBR, and direct tension. This table shows some of the typical temperatures and the parameters that are obtained doing these experiments and the criteria to grade the asphalt binder. In this example, we would like to learn whether the binder that we tested in example 5.1 can satisfy the requirements for low temperature cracking. The SuperPav requirement for this based on performance grading system is that the stiffness value should be less than 300 megapascal and the M value at the time of 60 seconds should be more than 0.3. Using the data from example 5.1, the stiffness value was obtained as 237.68 megapascal and M value was obtained as 0.311. So based on these values, the binder meets SuperPav requirements. This example requires constructing the master curve for an asphalt binder for a reference temperature of 25 C. In this table, the results from the DSR test are given for different frequencies and testing temperatures which should be converted to a reference temperature. This slide shows the different steps involved in constructing the master curve. We start with assuming shift factors for each temperature. Then we compute the reduced frequency for each temperature. We check if the plot of G star versus reduced frequency follows the expected tendency of the curve at the reference temperature. If not, steps 2 and 3 should be repeated as necessary. Then we fit the shift factors to a William-Landau-Ferry equation, which is given on this slide. This plot shows the complex shear modulus versus frequency and reduced frequency obtained from DSR tests, the values which were given in previous slide. This plot shows the master curve for the complex shear modulus at a reference temperature. So basically, all the values in previous slides were converted into the values at a reference temperature, which is 25 C. This slide shows shift factor versus temperature. Note that the master curve requires this relationship between shift factors and temperature. In this example, the results on testing of a binder using different criteria are given, and we are interested in determining if the binder meets specifications for rotting, fatigue cracking, and low temperature cracking. After comparing the test results with the requirements based on specification, we see that the binder does not fully meet any of the three performance criteria. Temperature susceptibility refers to the degree to which the properties of asphalt binders change with variations in temperature. Asphalt binders, as we discussed before, are viscoelastic materials, meaning they exhibit both elastic, solid-like, and viscous, fluid-like behaviors depending on the temperature. As the temperature changes, the binder's ability to resist deformation or flow also changes, and this variation is known as temperature susceptibility. At high temperatures, asphalt binders tend to behave more like viscous liquids, meaning they flow more easily and become softer. This can lead to rotting or permanent deformation in the pavement. At low temperatures, asphalt binders become more brittle and behave like elastic solids, which can lead to issues such as thermal cracking as the pavement contracts. Temperature susceptibility measures the sensitivity of the binder to these temperature changes and helps in understanding how well the binder will perform in different environmental conditions. This is important because asphalt pavements are exposed to a wide range of temperatures during their service life, from hot summer days to cold winter nights. A binder that is highly temperature susceptible may perform well in one temperature range but fail in another. For instance, in hot climates, a temperature-susceptible binder might soften too much, causing the pavement to deform under the weight of vehicles. Or in cold climates, the same binder could become too stiff and brittle, leading to cracks when the pavement contracts due to cold temperatures. The ideal binder is one that maintains consistent performance across a wide range of temperatures, providing sufficient flexibility at low temperatures to resist cracking and enough stiffness at high temperatures to resist rotting. There are different factors affect the temperature susceptibility of asphalt binders. For example, the first one is the asphalt composition. The molecular structure of the asphalt binder, including the presence of asphaltenes, resins, and maltines, determines how sensitive the binder is to temperature changes. Binders with a higher concentration of asphaltenes tend to be more temperature resistant because asphaltenes contribute to binder stiffness. Resins and maltines, on the other hand, make the binder more fluid, increasing its susceptibility to temperature changes. The other factor that affects the temperature susceptibility of asphalt binders is penetration index. The penetration index is a measure of a binder's temperature susceptibility. It is calculated based on the penetration values at different temperatures. A higher penetration index value or a higher PI value indicates lower temperature susceptibility, meaning the binder is more resistant to softening at high temperatures and hardening at low temperatures. A lower PI value indicates higher temperature susceptibility, meaning the binder is more sensitive to temperature changes. Another factor that affects the temperature susceptibility of the binders is viscosity. Binders with higher viscosity at higher temperatures tend to have lower temperature susceptibility because they are less prone to softening and flow. Similarly, binders that maintain a relatively low viscosity at low temperatures are less likely to become brittle, indicating better performance in cold climates. Other factor that affects or that can be used to study the temperature susceptibility of asphalt binder is performance grading system. The PG system explicitly accounts for temperature susceptibility by evaluating how the binder performs across a range of high and low temperatures. Binders are graded based on the maximum and minimum temperatures at which they are exposed to perform without excessive deformation for cracking. Several tests are used to evaluate temperature susceptibility in asphalt binders. The first one is the penetration test, viscosity tests as we discussed, dynamic shear barometer, and using the performance grading system is the other one. Bending beam barometer is other test that can be used to study the temperature susceptibility of asphalt binder. To reduce the impact of temperature susceptibility, engineers can apply a wide range of uh, let's say techniques. For example, they can use polymer modified binders. Adding polymers to asphalt binders improves their ability to maintain performance across a broader range of temperatures. Polymers increase the binder's elasticity, allowing it to recover more easily from deformation and preventing rotting at high temperatures while remaining flexible at low temperatures. The PG system offers a way to select binders that are optimized for the specific temperature ranges they will experience. For example, a PG 64-22 binder is designed to resist rotting at temperatures up to 64 C and cracking at temperatures as low as -22 C. The other technique to improve the temperature susceptibility of the binder is to use blend binders. In some cases, binders from different sources or with different properties can be blended to create a material with lower temperature susceptibility. This allows for better performance in regions with extreme temperature fluctuations. The use of additives is another technique to improve the temperature susceptibility of asphalt binders. Certain chemical additives, such as anti-stripping agents or oxidation inhibitors, can help improve the binder's resistance to aging, which in turn reduces its temperature susceptibility. These additives can also enhance the binder's flexibility and stiffness, making it more resistant to the adverse effects of temperature change. So as we mentioned in previous slide, modification is a technique to improve the temperature susceptibility of asphalt binders, and in general it can be used as a technique to improve the rheological properties of asphalt binders. Modified binders are commonly used to enhance the elasticity, stiffness, and overall performance of asphalt binders. Polymers such as SBS are added to the binder to improve its resistance to rotting, cracking, and aging. The inclusion of some modifiers allows the binder to recover more effectively from deformation, making it more resistant to permanent deformation caused by heavy traffic. Modification can also help to improve low-temperature performance. For example, polymer-modified binders remain flexible at low temperatures, reducing the risk of thermal cracking in cold climates. Polymer modification is widely used in high-traffic areas, bridge decks, and regions with extreme temperature fluctuations to improve the durability and overall performance of pavements. Some of the benefits of modifications are that, first of all, modification increases rotting resistance. At high temperatures, the binder remains stiff enough to resist rotting, which is critical for preventing permanent deformation under heavy loads. Modification can also enhance fatigue resistance. For example, polymers improve the binder's ability to withstand repeated loading without developing fatigue cracks, extending the pavement's service life. Moreover, modification can help to improve low-temperature flexibility. In cold climates, polymer-modified binders are less likely to crack, improving thermal cracking resistance. Overall, by using polymer-modified binders, engineers can design pavements that are more resilient to both environmental stresses and heavy traffic loads, reducing maintenance and repair costs. In evaluating the resistance to permanent deformation, the repeated and recovery test is recommended to estimate the rate of accumulation of permanent strain in pavements. This test simulates repeated loading similar to what pavements experience under traffic and assess how much permanent deformation the material accumulates over time. To model this behavior, the dashpot elements in the viscoelastic representation is used to capture the material's time-dependent permanent deformation. The part of the compliance is calculated after a certain number of cycles, providing insight into the material's tendency to accumulate strain under repetitive loads. A key measure derived from this test is the inverse of compliance, often referred to as stiffness. The stiffness is suggested as an indicator of the material's resistance to rotting. Materials with higher stiffness are better able to resist permanent deformation, making them more effective in preventing rotting under traffic loads. Therefore, higher stiffness values are generally associated with better long-term performance in terms of preventing rotting and deformation. Fatigue parameter can be obtained from a plot of ratio between accumulated dissipated energy divided by the energy dissipated in current cycle as a function of number of loading cycles as shown in this slide. Fatigue cracking in asphalt pavement is a common form of distress caused by repeated traffic loading over time. The development of fatigue cracking generally follows three distinct stages, from the initial formation of small cracks to the eventual failure of the pavement surface. These stages are critical for understanding how pavements deteriorate under cyclic loading and for implementing effective maintenance strategies. In the first stage of fatigue cracking, small microcracks begin to form due to tensile stresses in the lower part of the asphalt layer. This typically occurs at the bottom of the asphalt layer, where the pavement experiences the most tensile strain due to repeated traffic loads. Even though the stress applied in each cycle might be below the material's strength, over time the cumulative effect of repeated loading causes microcracks to initiate. In the second stage, the microcracks that formed in stage 1 start to propagate upward toward the surface of the pavement. As the cracks grow, they combine to form larger, more visible cracks, and the propagation of cracks is accelerated by continued loading, especially in areas with heavy traffic or overloaded vehicles. In addition to traffic loading, temperature fluctuation can also influence the speed of crack growth, as cold temperatures make the asphalt more brittle and prone to cracking. In the final stage of fatigue cracking is when the cracks on the surface of the pavement start to interconnect, forming a network of cracks that often resembles an alligator's skin. At this stage, the pavement has lost much of its structural integrity, and its load-carrying capacity is significantly reduced. Low-temperature cracking, also known as thermal cracking, is a form of distress that occurs when asphalt pavements are exposed to extremely cold temperatures. This type of cracking is a significant issue in regions that experience harsh winter conditions or large temperature fluctuations. Unlike fatigue cracking, which is caused by repeated traffic loads, low-temperature cracking occurs due to the thermal contraction of the pavement. Several tests are used to evaluate the low-temperature performance of asphalt binders and mixtures. These tests can help engineers to select materials that will resist cracking in cold climates. For example, the BBR test is used to measure the flexural stiffness and creep rate of asphalt binders at low temperatures. The binder sample is cooled to a specified temperature and the load is applied to the sample. The test measures the binder's ability to deform without cracking under low temperature conditions. Direct tension test is another test that is used to measure the tensile strength of asphalt binders at low temperatures. The binder is subjected to a direct tension until it breaks, simulating the stress conditions that lead to thermal cracking. The results of the direct tension test provide insight into the tensile failure strain, indicating how much deformation the binder can withstand before cracking. Volumetric properties of asphalt mixtures are critical in determining the performance, durability, and long-term behavior of pavements. These properties relate to the proportion of various components um, like asphalt binder, air voids, and aggregate within the mixture. Proper control and understanding of these properties ensure that the asphalt mix can withstand traffic loads, resist environmental damage, and maintain its structural integrity over time. GMB represents the specific gravity of the entire compacted asphalt mixture, including both the aggregate and asphalt binder as well as the air voids. In this slide, GMB is a function of the dry weight compacted sample in air and weight of asphalt mixture in saturated dry condition and weight of sample underwater. GMM or Rice specific gravity represents the specific gravity of the mixture when it is compacted to its maximum density with no air voids, that is, condition where the air void content is zero. This property is used to calculate air void content and assess the degree of compaction. Air voids are calculated using the specific gravities of the mixture. The air voids represent the empty spaces in the mixture that are not filled with asphalt binder or aggregate. Air voids represent the volume of air spaces within the compacted asphalt mixture, usually expressed as a percentage of the total volume. Air voids are important because they provide a space for the expansion and contraction of the asphalt due to temperature changes. Proper air void content helps prevent pavement cracking and rotting while allowing the mixture to resist moisture damage. Typical target values for air voids in asphalt mix are around 4% for dense graded mixes, though this can vary based on the specific applications or local standards. If air voids are too low, that is a mixture um, or in other words, the mixture is overcompacted, there is insufficient space for expansion, leading to bleeding and rotting. If air voids are too high, the pavement can become permeable, allowing water to infiltrate, which can lead to moisture damage and freeze-thaw damage in cold climates. Excessive air voids also weaken the structure, leading to early cracking. VMA, voids in mineral aggregate, is calculated using the specific gravities of the aggregate and the compacted mixture. It represents the total void space between aggregate particles that must be filled with asphalt binder. VMA is the volume of void spaces between the aggregate particles that must be filled with asphalt binder. It is expressed as a percentage of the total volume of aggregate in the mix. VMA ensures that there is adequate space within the aggregate structure for the binder to coat the aggregate particles, ensuring good adhesion and overall mixture stability. Proper VMA ensures that the mixture has enough binder to create a durable, flexible, and well-bonded pavement layer. VMA must be controlled because too little binder or low VMA may lead to brittle pavements that crack under loading, while too much binder may lead to rotting and bleeding. Depending on the aggregate gradation and nominal maximum aggregate size, there are VMA or minimum VMA requirements specified by the agencies like the American Association of State Highway and Transportation Officials or local standards. GSP is the specific gravity of the aggregate, including the volume of both the aggregate's solid material and its permeable pores that absorb asphalt binder. This property is important for determining how much asphalt binder will be absorbed by the aggregate versus how much will remain available to coat the aggregate particles. VFA, voids filled with asphalt, is the percentage of VMA that is filled with asphalt binder, representing how well the air voids and aggregate particles are coated by the binder. VFA is important because it reflects the balance between binder and aggregate in the mixture. A high VFA means that more voids in the aggregate are filled with binder, which can enhance durability and resistance to air and water infiltration. Effective specific gravity of aggregate is defined as the weight of aggregate divided by effective volume of aggregate. Asphalt absorption refers to the amount of asphalt binder that is absorbed into the pores of the aggregate during the mixing process. This is important because the absorbed binder is not available to coat the aggregate and contribute to the mixture's performance, such as providing flexibility and durability. Asphalt absorption affects the effective asphalt content in the mix, which is critical for proper binder coverage and pavement performance. So in this slide, we see how to determine asphalt absorption. In this example, you are given um, 5 properties of a compacted hot mix asphalt specimen measured at 25C. Using these values, this example requires you to determine all volumetric properties as we discussed in previous slides. These properties, for example, include VMA, VFA, VA, so on and so forth. After applying previous equations and using the values given in previous slide, we can calculate all volumetric properties of the asphalt mixture as shown in this slide. An asphalt mixture property refers to the specific characteristics or behavior of an asphalt mix that determine how it performs under various conditions such as traffic loads, temperature fluctuations, and environmental exposure. These properties are essential in predicting the durability, strength, flexibility, and resistance to distress of asphalt pavements. There are different types of asphalt mixture properties mm, that can be determined using a wide variety of testing protocols, such as dynamic modulus, creep compliance, repeated dynamic, indirect tension, and beam fatigue. The dynamic modulus represents the stiffness of the asphalt mixture under repeated traffic loading and is critical property in predicting pavement performance. A higher dynamic modulus indicates that the asphalt mixture can better resist deformation, making it ideal for high traffic areas. The dynamic modulus is influenced by factors such as temperature and loading frequency, with stiffer mixtures typically performing better under heavy traffic. According to the Ashton specification, the dynamic modulus is measured at different temperatures and loading frequency. This slide shows the decomposition of loading and strain response into dynamic and creep. This slide shows the dynamic modulus apparatus. Test is conducted from lowest to highest temperature and from highest to lowest frequency of loading. There are three LVDTs to measure the response, and this apparatus applies the load on the specimen to observe the response. Data from dynamic modulus test can be used to compute the master curve of hot mix asphalts. One recommended procedure to mathematically represent the master curve is using sigmoidal function as shown in this slide. Curve compliance measures the time-dependent deformation of asphalt mixtures under constant stress, providing insights into the material's ability to resist permanent deformation. Mixtures with lower curve compliance are stiffer and less likely to rot under sustained loads, making them suitable for areas with heavy traffic. Curve testing helps evaluate how the mixture will perform under long-term loading conditions, particularly in hot climates. This slide shows the curve compliance response of hot mix asphalt in three different zones: primary zone, secondary zone, and tertiary zone. The repeated dynamic test subjects the asphalt mixture to cyclic loading to simulate real-world traffic conditions, assessing the mixture's fatigue resistance and rotting performance. This test helps predict how well the mixture can withstand repeated traffic loads without developing fatigue cracks or permanent deformation. The results of this test are critical for designing mixtures that can endure the stresses of high-traffic environments. This slide shows how to describe the results of repeated dynamic tests. Flow number and slope are similar to curve tests, but replacing time by number of cycles in the x-axis. The indirect tension test measures the asphalt mixture's resistance to tensile stresses, which are responsible for cracking at low temperatures or under heavy traffic loads. The test applies a compressive load to a cylindrical sample, inducing tensile stress in the horizontal direction, allowing for the evaluation of low-temperature cracking resistance. The test is particularly important for designing asphalt mixtures in regions prone to thermal cracking under cold environmental conditions. The beam fatigue test evaluates the asphalt mixture's ability to resist fatigue cracking under repeated bending or flexural loads. In this test, an asphalt beam is subjected to cyclic loading until failure, helping to determine the mixture's fatigue life and performance in the field. Beam fatigue testing is essential for designing long-lasting pavements that can withstand repeated traffic loading without cracking. This slide shows the beam fatigue apparatus and its different parts. In beam fatigue tests, damage can be determined in stress control mode or in strain control mode, and measurements are used to plot several relationships between the number of cycles to failure and stresses or strains. This example, bilateral tests conducted on a beam specimen in strain-controlled mode. The specimen has the reactions of 12 inch apart. Initial bilateral stiffness of the mixture is 450,000 pounds per square inch. So based on these results, you are required to determine the initial applied load and the beam deflections at each strain level. You are also required to determine coefficients of equation of strain versus cycles at failure. So for this, you need to use the equations in previous slides to determine these parameters. So using the previous equations that we learned in previous slides, we know that at a fixed strain level, the initial stress can be calculated using Hooke's law, where E is the initial flexural stiffness of the beam. We can use sigma sub naught to obtain the initial total load applied by using the equation that is given in this slide. Then we can use P to obtain the initial dynamic deflection at the center of the beam, for which we need to have the moment of inertia of the beam. We can get the value of the moment of inertia using the values of the dimensions of the beam. By doing so, we can obtain the results and basically P and D values for different strain levels. Then by having the results from previous table, we can plot the log number of cycles to failure versus log of 1 over strain. So this can be done by taking logarithms of the equation, and we can plot the results as shown in this graph. In summary, in this chapter, principles of the chemistry of asphalt binders and the chemical model for binders were described. We learned about different properties of asphalt binders and asphalt mixtures and how to measure those properties using different experimental protocols. We also learned about different techniques to classify asphalt binders based on their rheological properties, based on their physical properties. We learned about the volumetric properties of the asphalt mixture and how these properties can help us in designing an asphalt mixture that can resist a wide range of loading conditions, temperature conditions, and basically these properties can help us in designing a pavement with long-term high quality performance.